Good, good morning, students. Welcome to video lecturing class on control engineering. So today we'll start with the third module. So in that, first we'll begin with the root locus. So this method is introduced by W.R. Evans in the year 1948. So this is a graphical method in which the moment of poles in the S-plane is sketched when a particular parameter of the system is varied from 0 to infinity. Okay. So the basic definition is, it is the locus of poles, that is for the closed loop, obtained when the system gain k is varied from minus infinity to plus infinity in characteristic equation. So to understand the basic concept of root locus, let us consider a system which is shown in figure. So here this g of s is the forward path transfer function. Okay, that is k into g dash of f s will be the transfer function of the forward path. That is, these are in series, so you have to write the product. So now if you consider g of s into h of s is the open loop transfer function of a system. So for such kind of system you can write the characteristic equation as 1 plus g of s into h of s, which is equal to 0. It is going to be your characteristic equation. Now if you consider the gain for the same equation, you can rewrite it as 1 plus k into g of s into h of s equal to 0. So here the roots of this equation are called closed loop poles. So when the k is varied, the roots will change, that is, roots are dependent on the value of k. So if k is varied from minus infinity to plus infinity, different roots will occur. If all such roots are located on S plane, and if you join them, then the resulting locus or the resulting graph or the resulting path, you can call it as root locus. There are two types of root locus. One is direct root locus and another is inverse root locus. So in case of direct root locus, if the value of k is varied from 0 to infinity, then resulting root locus is a direct root locus. That is, the gain value will be only from 0 to infinity. Generally, the direct root locus is called as a root locus. And inverse root locus, second one is, if the value of k is varied from minus infinity to 0, then you can call the resulting root locus as inverse root locus. And in earlier discussion I mentioned one term, S plane. So what do you mean by S plane? So first we need to understand that. So S plane is a plane whose abscissa is a real and ordinate is an imaginary axis. That is, x axis is a real axis and y axis is imaginary axis. So if you consider an example, that is, obtain the root locus for a system whose open loop transfer function is, that is, g of s into h of s equal to k by s. So here this is the given transfer function for the open loop. So now for this transfer function, you can write the characteristic equation as 1 plus g of s into h of s equal to 0. So here g of s into h of s is nothing but k by s. Substitute that. So we will get k plus s equal to 0 or s equal to minus k. So now to obtain the root locus, we must vary k from 0 to infinity and need to find out s value. So if you substitute the k value from 0 to infinity, you will get the s value as from 0 to minus infinity. So now to locate these values on S plane, it is the negative real axis of the S plane is a root locus, because your all S values are negative here based on the k values. Okay, so this is the root locus part. Now one more condition is there, that is angle condition. So these conditions are used to determine the actual roots of the equation. Okay, so that is, for all s values you can represent or you can express those values in terms of complex numbers, that is sigma plus j omega. So for any value of s, if it has to be on the root locus, it must satisfy the characteristic equation. So here we are having the characteristic equation as 1 plus g of s into h of s equal to 0, or g of s into h of s equal to minus 1. So therefore the s plane is a complex here. So we can represent it as g of s into h of s equal to minus 1 plus 0j, where this j value is root of minus 1. So now let s be on any point, that is here, and angle, you can write it as, that is angle of g of s into h of s as tan inverse of imaginary part divided by real part, that is 0 by minus 1. So in this equation, imaginary coefficient of imaginary is this one and real part is this one, minus 1. So tan inverse of 0 minus 1 will be 0. But general solution for that g of s into h of s equal to angle of g of s into h of s is equal to plus or minus 2q plus 1 into 180 degree. So therefore we can represent all the s values in terms of sigma plus j omega, that is complex, and also becomes the complex number. So if any point on S has to be on a root locus, it must satisfy that characteristic equation. So now if any point S of the form sigma plus j omega has to be on a root locus, then should satisfy angle of g of s into h of s, where s is a complex term, sigma plus j omega should be equal to plus or minus 2q plus 1 into 180 degree, where q is starts from 0, 1, 2, so on. That is odd multiple of 180 degrees. So this is called as angle condition. Similarly, for the magnitude condition, a point s equal to sigma into j omega is said to be on a root locus if the magnitude of g of s into h of s at that point is unity. That means its value should be equal to 1. If you take the value of that complex number, that is by writing the determinant, that is determinant of g of s into h of s, where s is sigma plus j omega equal to 1, but in general k will be unknown. So if the point satisfies the angle condition, then it satisfies the magnitude condition also, because in your characteristic equation you are having that k as unknown. So in that case it is very difficult to apply this magnitude condition. Either of the condition it should satisfy for the value, particular value of s, which has to be on root locus. So now there are, you need to remember few steps from the 10 steps to plot the root locus. So the first one is, remember root locus is always symmetrical about the real axis. That is, the function should be of the form g of s into h of s. If the transfer function is c of s by r of s is given, then you need to convert it into form of g of s divided by 1 plus g of s into h of s, and from that you need to find out the g of s and h of s. If second one is, if g of s into h of s is of the form k into s plus a, s plus b, the numerator, divided by s plus p, s plus q, so on in the denominator, where a, b, c and p, q, r are the constants, then the roots of the numerator are known as zeros and the roots of denominator are known as poles. That is, whatever the roots you are going to get from this numerator terms are zeros, and whatever the roots you are going to get from the denominator terms are called as poles. And while determining the values of p and z, you need to consider the k value. So if p equal to, that is the number of poles, is equal to say 0, that means there are no terms associated with s in the denominator. So not roots, just number of roots it is p. Okay. Z is also number of zeros, not the actual values. For example, there are 3 terms in the denominator. Okay, so that time your equation will have 3 roots. So that value 3 is nothing but your p. Okay, and if p is greater than z, then the number of root locus branches are equal to p, which are equal to number of poles. If z is greater than p, that is number of zeros are greater than number of poles, then the number of root locus branches are z, that is equal to number of zeros. Then you need to find out the poles and zeros, that is particular value of their roots in the numerator and the denominator. Then you need to locate them on the S plane. If p equal to z, that time the number of branches are equal to p equal to z. And always root locus branch starts from a poles and ends at the 0 or ends at the infinity. That is, while drawing the root locus, your starting point should be pole and end point should be 0. If there are no zeros, that time you should end towards the infinity. Then the third step is find out which part of the axis is root locus. So first you need to convert the given equation into characteristic equation. Then you need to find out number of poles, number of zeros and number of branches based on the values of p and z. Whichever is greater, that value is going to be equal to number of branches. After that you need to find out their respective values, that is you need to find out the roots. Then you need to find out which part of the axis is a root locus. To do this, consider part on a real axis. Now this point is said to be lies on a root locus if the sum of the number of open loop poles and open loop zeros on the real axis to the right hand side of this point is an odd number. That is, for example, here I am having p, q, r, s, t are the roots. So I have located on this one. So now in between these two I will consider a part. So right side means this side, that side you need to take summation of number of poles and zeros. Okay, so here this is the example. Poles from the denominator, zeros from the numerator. So their respective values are, zeros are -1 and -4, poles are 0, -3 and 5, -5. So here p is greater than z. Okay, located all the values here, -1, -3, -4, -5 and 0. So now if I consider this part here, that is between this point and this point, one section. So towards the right side you have to take the summation of p and z. If that summation is an odd number, that time you can consider this portion as the root locus part. So here if I consider this one, there is only one pole. Okay, so 1 is an odd number. That means from 0 to -1 it is a root locus part. Now I will consider a section between -1 and -3 here, like this. Then take the summation of p and z towards the right side. So there is 1 0 and 1 pole. So 1 plus 1 is equal to 2, which is a even number. That means from -1 to -3 it is a non-root locus part, that is NRL. Now consider a section between -3 and -4 here. Now take the summation of p and z towards right side. So the reference section is here, 1 pole, 1 0 and another pole. So that means there are summation is 3, which is an odd number. So -3 to -4 it is a root locus part. Then consider a section between -4 and -5 here. Then take the summation of p and z towards the right side. So -4, -3, -1 and 0. That means the summation is equal to 4, which is a even number. So -4 to -5 it is a NRL. Now between -5 and infinity if you consider, so the summation of p and z will be 5, which is an odd number. So from -5 onwards it is a root locus portion. Okay. Then the next rule is, generally the number of poles, that is p, will be greater than zeros. That is, if p is greater than 0, then p minus z is the number of branches will approach infinity. Okay, so you need to find out the number of branches which are tending to infinity. That value you will get to know by taking the difference between the poles and zeros, that is p minus z, and they do so along the straight line called asymptotes. Okay, so if you want to determine the number of asymptotes, you should know p and z value, and their differences value will be the number of asymptotes. If p equal to z, then there will be no asymptotes, that is all branches will start at poles and ends at 0. Not a single branch tends to infinity. Then you need to find out the angles for those asymptotes. So angle of asymptotes you can calculate by using this formula, theta equal to 2q plus 1 into 180 degree divided by p minus z, where p is number of poles, z is number of zeros, and this q value is, it will start from 0 and its value should be equal to difference between poles and zeros, or number of asymptotes, that is 0, 1, 2, 3, p minus z minus 1, here minus 1 because we are considering 0 here. Asymptotes are always symmetrical about their real axis. Then the fifth one is, need to find out centroid for those asymptotes. So all asymptotes intersect at a common point on a real axis called centroid, and you can calculate that centroid by using sigma equal to summation of real part of poles minus summation of real part of zeros divided by p minus z. So this centroid may or may not lie on a root locus. It is not meant always that centroid value should lie on a RL part, that is here. Previously I have determined this portion as RL, this as NRL. Your centroid either may come on RL or it may come on NRL. Then the sixth one is, need to find out the breakaway point. So it is a point on a root locus where multiple roots are of the characteristic equation occurs for a particular value of k. So to find out the breakaway point, you need to consider the given transfer function or given characteristic equation. So here let us consider the characteristic equation as k divided by s plus s. K divided by s into s plus 2. So here you can write it as characteristic equation as 1 plus k divided by s into s plus 1. If I simplify that, I will get it as s square plus 2s plus k equal to 0. So from this I can get the values of roots, that is s equal to minus 1 plus or minus square root of 1 minus k. So here if I substitute different k values, for those k values your s values are going to vary. That is, if you substitute k as 0, one root will be 0, another root will be minus 2, and likewise it is 0.29 you are getting here, minus 1.7 you are getting, minus 1, minus 1.1 plus 2j, minus 1 plus 2j. So here just by general prediction I can take this k value as the value breakaway point. That remember, the breakaway point should lie on root locus part. Okay, so in this there are three steps or three procedures to determine the exact location of breakaway point. So in this equation, when k equal to 1, both s1 and s2 will occur at a point minus 1. So this point is called as breakaway point. So prediction of that such kind of breakaway point helps to reduce the calculation. So first one is general prediction for a breakaway point. If there are two adjacently placed poles on a real axis, then the axis between them is a part of a root locus, then there exists a minimum one breakaway point. So here this RL will have the one breakaway point. In this case, the root locus branches will approach towards the breakaway point, that is inward. Towards that breakaway point they will approach. Then if there are two adjacently placed zeros on the real axis and the axis between them is a part of a root locus, then also there exists a minimum one breakaway point. If there are two zeros, and if you find this portion as the root locus portion, so that time between these two there will be a breakaway point. But in this case, the root locus branches will move away from the breakaway point. They will tend to 0 side. In case of pole, they will tend towards breakaway point. Here they will tend move away from the breakaway point. If there is a 0 on a real axis and to the left of that there is a no pole or a 0 existing on the real axis, and the complete real axis to the left of this 0 is part of root locus, then there exists a minimum one breakaway point. Similarly, if you take this one as a 0, okay, this one as the pole, and after that if it is tending to infinity, so here also we can consider one breakaway point will exist. So now we know whether breakaway point exists or not. If it is there, then we have to find out the location, that is exact location of that breakaway point. So to determine that exact location of the breakaway point, first we need to write the characteristic equation in the form 1 plus g of s into h of s equal to 0. We separate k from this equation, that is we need to, in this term we will be having k, so we need to simplify that equation in terms of k equal to the remaining terms. Then you need to differentiate k with respect to s, and you should equate that one to 0, dk by ds equal to 0. Then find the roots of this equation, that is the values of s. After getting the roots, you need to substitute those values in s in the equation of k. If that k comes positive, then it is a valid breakaway point. If that k comes negative, then it is not a valid breakaway point. If that s is a complex, then you need to use angle condition to check the validity. That is, wherever s is there, you need to substitute it as sigma plus j omega. If it satisfies the angle condition, that is, if you get that angle as odd multiple of 180 degree, then find k using the magnitude condition. If it is, that is, determinant of g of s into h of s equal to 1, then the root locus approaches or leaves the breakaway point at an angle of plus or minus 180 degree divided by n, where this n is the number of branches approaching to breakaway point. After that, once you find out the breakaway point, you need to find out intersection of root locus with imaginary axis. So sometimes root locus cuts the imaginary axis. The point of intersection is found by using roots array criteria. That is, for that, let us consider the equation 1 plus g of s into h of s equal to 0. Construct the roots array in terms of k. Find k marginal by selecting one of the row in the roots array, which makes the entire row as 0 except s raised to 0 row. Find the auxiliary equation, that is a of s equal to 0, by using coefficient of a row which is just above the row of zeros. Then you need to put that k marginal value in the k equation, that is in the auxiliary equation, and find the roots of the equation. Then the roots are the point of intersection of the root locus with imaginary axis. For example, if this is the characteristic equation, for this characteristic equation, first you need to construct the roots array. So there are, it is s cube is there, the highest degree. So s cube, s square, s raised to 1, s0. First you need to write this one. So here, first we will write the coefficient of s cube. Then in the second place, you need to write the coefficient of s. Skip this s square, write the s, coefficient of s. Then further you don't have anything, you can write that 0. Similarly for s square, first you need to write the coefficient of s square. Then skip this s term and write the coefficient of another term, that is k. Okay, so that is conjugative values you have to write. Then s raised to 1 you need to write. Okay, so for that you cannot write this 4 because already you have written here. So for that, first you have to take the cross multiplication of 5 into 4, 20 minus this into this, okay, divided by this term. Okay, so for example, this is A, B, C, D. Okay, B into D minus A into C divided by B, that is 5. And here if you apply the same rule, K into 0 will be 0, 4 into 0 will be 0, no need to worry. Then here S raised to 0, again we have to apply the same thing, this into this minus this into this. So here this 20 minus K divided by 5 into K minus 5 into 0 will be 0 divided by 20 minus K by 5. So here in the numerator and denominator you are going to have 20 minus K by 5. So both the terms will vanish. We are going to left with the K value. Okay. So since S raised to 0 cannot be 0, we need to leave this row. Let us consider this row to get the auxiliary equation. Now if 20 minus K divided by 5 becomes 0, then entire row becomes 0. So for that reason 20 minus K divided by 5 equal to 0, or K marginal is 20. So now in the auxiliary equation, that is A of S equal to 0, the auxiliary equation is the immediate next row. So first you have to ignore this one. From this you need to find out the auxiliary, K marginal, and that value you have to substitute in the auxiliary equation. So to write the auxiliary equation you have to consider this row. So it is 5 into S square plus K is the auxiliary equation. So 5 into S square plus K, and in place of K you substitute this K marginal. From that you will get S square as minus 4. So S is plus, the root of this one will be plus or minus 2j. So therefore S equal to plus or minus 2j is the point of intersection of the real root locus with the imaginary axis. Then you need to find out angle of departure at complex poles. In some of the problems you may get the poles value as the complex roots. So in such cases you need to find out the angle of departure. That is, if there are complex poles are present, then the angle of departure has to be found out, and the root locus leaves the complex pole tangentially to the line at an angle of theta d. To find this, you need to join all the poles and zeros to the pole whose angle of departure has to be found out using the straight line. Then find the contribution of angles made by each pole and zeros. Then you need to find out the summation of sum of angle of made by poles and sum of angle made by zeros. That is, first I have located all the poles and zeros. For example, here my P2 and P4 are the complex poles. So I will take this pole as the reference pole, and to this pole I need to join all the poles and zeros with the straight line. From that you need to find out the values of pi p and pi z. Then pi is given by summation of pi p minus pi z. Then the angle of departure pi d is given by 180 degree minus pi. Okay. So this pi is summation of pi p minus pi z. So this angle of poles and angle of zeros you will get by joining all the poles and zeros to any one of the complex pole or zero. Angle are must measured in clockwise, counterclockwise direction. Then it is a positive value. If it is a negative, then it is measured in clockwise direction. So the angle of departure for the conjugate pole, which is a pair of the P2, that is the P4, is exactly same value but opposite sign, because complex means there will be two values, one with plus and one with minus. You need to find out if for any one of the pole. For example, if you get angle of departure as say 75 degree for P2, then for P4 it will be minus 75 degree. Then you need to find the ninth step is angle of arrival at complex poles. Instead of poles, if there are complex zeros, then you need to find out the angle of arrival. So if there are complex zeros, then the angle of arrival has to be found out, and the root locus approaches this zero tangentially to the line at an angle of pi a. To find this you need to follow the same procedure, but the only change is here angle of arrival phi A is 180 degree plus phi, where phi is summation of phi p minus phi z. And the last step is need to write the comment. If the k value is greater than 0 and less than k marginal, your system is stable. If the k is equal to k marginal, the system is marginally stable. If the k value is greater than k marginal, then the system becomes unstable. So at the end you have to write this comment. Once you find out all these values, you need to plot the root locus. Okay. So here there are 10 steps you need to remember. The very first one is, first you need to check whether the given equation is in the standard format or not. If it is not, then you need to convert that one into a standard format. After that, then you need to find out the number of poles and number of zeros. Zeros are nothing but the terms which are in the numerator. Poles are nothing but which are in the denominator. Then you need to find out their values, actual root values. And you need to find out the number of root locuses, branches. So that is based on the values of p and z. If p is greater than z, then number of root locus branches will be equal to p value. Then you need to find out the values of poles and zeros, and you need to locate those values on the S plane. After that, the third step is need to find out which portion is a root locus and which is an NRL. Then need to find out the number of asymptotes which are tending to infinity. So that value will get by taking the difference between the number of poles and zeros, p minus z. Okay. After that, if you find out the number of asymptotes, then you need to find out the angle of for those asymptotes by using this formula, theta equal to 2q plus 1 into 180 degree divided by p minus z. After that, once you find out the number of asymptotes and their respective angles, you need to find out the centroid for those asymptotes. So that value you need to find out by using this formula. And remember, centroid may be on NRL and may not be. It is not meant that always the centroid should lie on root locus portion. Then you need to find out the breakaway point. So the general prediction is always your breakaway point will lie on root locus part. Okay. But to find out the exact location of that root locus, you need to consider this one, or you need to go through this procedure. One, you have to consider characteristic equation, simplify that one for the k equal to, then take the differentiation dk by ds and equate that one to 0. From that you will get the value of s. Okay. Substitute that s value back to k equation. If you get that k as a positive, then it is a valid breakaway point. If it is a negative, then it is an invalid breakaway point. If it is that value is a complex root, here if you get this root as complex root, then at that time you have to use angle condition to check the validity, and it should satisfy the magnitude condition. Then the seventh one is the intersection of root locus with imaginary axis. Since if it is tending to infinity, that time definitely it has to cut the imaginary axis. So for that one, you need to construct the roots array. Then you need to find out the auxiliary equation. From that auxiliary equation, you will get the value of intersection with imaginary axis. Okay. Then if there, and this, remember, this 8th and 9th steps are you have to use only when if the poles and zeros in the very first step, if you are getting those values in any one of the value are complex terms, only that time you have to go with this angle of departure if the poles are complex. If the zeros are complex, then you have to go with this angle of arrival. Otherwise, directly we can skip this 8th and 9th step. Then you need to plot the root locus. After that, you have to write this comment based on the k value. So you try to go through these 10 steps, try to understand and try to remember these steps. For any type of problem, these are the steps which you need to go through to get the solution. Okay. If you have any query, you can put the comment in comment box. Thank you.